Okay, sure. Hey, I'm Zhihao. So today I'm going to talk about our techniques for integrating external resource into Legion. So as for the motivation, so Legion used to assume a closed world, which means all the data instances are generated and manipulated inside Legion runtime. But this is not always true because there are cases when the application do need to interact with some external data. So for example, your application may need to load some input data from files on disk, or it has to checkpoint some intermediate result back to some persistent storage. So the other cases could be the application may need to interact with some databases. And this brings a challenge into Legion runtime because the external interaction could be very expensive, especially when, in the case when the data is large, and the external I/O could take a significant proportion of the entire execution time. So in our original solution, Legion asked the user to manage external I/O at application level. So we allow the Legion to access external data inside Legion task. But this solution has both performance and correctness issue. So as for the performance, because doing the external I/O may block the computation thread, which may result in CPU underutilization. And it is also hard to hide I/O latency because if you do both I/O and computation inside Legion task, there's no space for Legion runtime to schedule the tasks to pipelining I/O and with computation. And it is also hard to control the resource utilization. So because if you, for example, if you are loading some data from disk files, then you have to do disk I/O at application level. And on the other hand, Legion also has a memory instance called disk memory, which is identical to CPU memory, but has a large capacity with relatively low bandwidth. And by the mapper interface, the application could decide to save some data into disk memory, and therefore the Legion low-level runtime may need to transfer data between CPU and disk memory. And doing the disk I/O at both application level and Legion runtime level may result in data contention and bad performance. And as for the correctness issue, because Legion doesn't provide data consistency and doesn't do any dependency analysis for the external data, and therefore the user has to manually control the external data consistency at application level. So we provide a new approach, so we think it's reasonable to define semantics for external resource inside Legion runtime to address both correctness and performance issue. So as for the correctness, we would like Legion to guarantee consistency and preservation of data dependencies. And for the performance, we would like Legion runtime to automatically perform all the optimizations for external resource. And so our idea is to integrate the external resource into Legion by mapping them to regions, and which the mapping is achieved by the attach operation. So the attach operation basically attach external resource to a region. So the external resource could be some normal files that is understandable by Legion, or it could also be some formatted files such as the HDF5. Or we also support attached to some opaque data structure. So here shows an example of attaching HDF file to logical region. So this is a runtime interface, and you need to provide the file name, which shows the path for the HDF file. And you also need to tell Legion which logical region you would like to attach to. And you also need to provide a mapping between fields in Legion to data sets in HDF5. So recall that the logical region is a production of index space and field space. So in order to attach HDF file to region, application need to make sure that the HDF data space must be identical to, must matches the index space in Legion, which means the size of each dimension should be the same in the HDF file and in the index space. And the application also needs to define how to map from fields to data sets in HDF5. So the semantic for attach operation involves two steps. The first step, because the logical region could have been previously mapped to some existing physical instance, and region cannot guarantee that the data in existing instance are identical to the data in the external resource. So the attach operation will first invalidate some external instance. And the second step, the attach operation will create a new instance inside region runtime, and that represents the external data. And it is worth to notify that there's no external I/O happens with the attach operation. So you just tell region runtime that you have created a new physical instance, and the external resource for that. So the attached region is being accessed by simultaneous coherence. So in the overview talk, we have been briefly introduced the simultaneous coherence. So to emphasize, the simultaneous coherence allows different tasks to access the region simultaneously. So here we would like to provide a relaxed coherence model so that could enable some potential parallelisms. And the simultaneous coherence requires that all tasks must use the only valid physical instance, so that to make sure that the updates are immediately visible to the other tasks. And region runtime puts copy restriction on the regions with simultaneous coherence mode, which implies that tasks cannot create local copies. So this is just to make sure that the updates are immediately visible to each other. And, but this may result to inefficient memory access for external resource. So for example, if you have attached some disk files to your logical regions, and this, so the copy restrictions means that every task that accesses the external file needs to go to disk and fetch the files, which could result in very bad performance. So to address this inefficiency, we provide the acquire and release operation. So the acquire and release are semantics to notify region runtime when it is safe to allow some local copies. So acquire operation basically notifies the region that, okay, at this point, it is safe to allow some local copies because we have guarantees proper synchronization at application level. And the acquire operation will remove the copy restriction, and therefore region could create local copies in any memory. And the release operation will just undo the effects of acquire operation. It will restore the copy restriction, and it will also invalidate all existing local copies and flush back dirty data back to the external resource. So here's an example of acquire and release operation. So assume that you have a logical region that is attached to an external instance on external resource, and if you would like to run tasks on different nodes that uses the external instance, the application could launch its acquire operation, which tells Legion that it's safe to make some local copies. So Legion runtime could decide to copy data from the external resource to different nodes and create some local instance. And therefore, the task could directly use the local instance. And when all the tasks that uses the external resource has been completed, and the application could launch a release operation, which tells Legion that it's time to invalidate the local instance and flush back the dirty data. And besides attaching to normal files and HDF files, we also support attached to in-memory opaque data structures. So there could be some, we support manipulating on some external data that comes from other applications. And this external data might be in a data form that is not understandable by Legion. So Legion support attaching opaque data structures to Legion. So for example, the field could actually be pointers or references to the opaque data structures. But one problem with the with this with opaque data structure is that the bitwise copy doesn't work in this case. So for example, if the fields are actually pointers to the opaque data structures, Legion runtime cannot just copy the pointers. So it needs some serialization and deserialization mechanisms for that. So Legion requires the custom serialization, deserialization methods for fields that requires non-trivial copies. So user needs to define a class with 4 methods. So the first method is just tell Legion, given a reference to the opaque data structure. So how much memory we need to serialize that data structure. And the next 2 methods just tell Legion how to serialize and deserialize the opaque data structure. The last one is to destroy the opaque data structure, because Legion may create some other local copies. And upon the completion, Legion needs to invalidate the local copies. So therefore, the application needs to tell Legion how to destroy the created opaque data structure. So the registration for serialization, deserialization operation is very similar to reduction operation. So there's a runtime API called register customer third-des operation. So basically, you just register that third-des object with an ID. And if you would like to specify some special fields that needs serialization or deserialization method, it's very simple. So when you allocate a field, so besides telling Legion that what's the size of that field and what's the field ID for that, you just need to tell Legion what's the serialization, deserialization ID for that. And after that, Legion will automatically use the serialization, deserialization methods when copy data that is attached to some opaque data structures. OK, great. No questions so far. Pretty good. OK, great. So we also implemented excuse me. We also implemented several optimizations for external I/O. So the first optimization is to integrate the external I/O into Legion's deferred execution model. So Legion runtime will manage and reschedule external I/O to maximize the resource utilization and also overlap the external I/O with computation. So we use matrix multiplication benchmark to evaluate the effectiveness of overlapping external I/O with computation. So the application will load some large input matrix from files and performs the matrix multiplication. And we have implemented 3 approaches. The first baseline approach, we would like to know how long it takes to perform I/O and how long it takes to do the computation. So the baseline approach will have an initialization phase, so which will load the entire matrix into logical regions before starting any computations, and which shows the time it needs on I/O and the time it needs on computation. And the in-task I/O approach just simulates our original solution, which is doing I/O inside Legion task. So in every Legion subtask, the beginning of every Legion subtask will load the data from files to logical region and then do the computation. And by doing the in-task I/O, we could overlap the I/O with computation at some point because different tasks might be executed at different speeds. So there could be some Legion tasks doing the I/O while the other Legion tasks doing the computation. So this could pipelining I/O and computation at some level. And the Legion plus external resource approach is our integration techniques. And so the Legion plus external resource approach will let the Legion runtime schedules external I/O and overlap it with computation. And as we can see, that the Legion runtime could perfectly pipelining I/O and computation, and there is almost no I/O blocking in this case. And the second optimization is reducing data transfer. Assumes that we have as the application, the region is attached with some external instance on node 1, and there are tasks that needs to be executed on node 2 for parallelism. So the acquire operation, the acquire and release operation allows Legion runtime to make some local copies. So the Legion runtime could just copy the external instance to node 2. And as a result, the task could just use the local instance. And upon the completion of the task 1, there could be some other tasks that also needs the external instance. Because Legion manages the consistency and availability of the external resource, the local copies. So Legion knows that, okay, this local instance has the most up-to-date version, and it has a better performance compared to the external instance. So the task 2 and 3 can just use the local copies instead of fetching data from remote server. So so we have designed a distributed graph rendering application for evaluating the effectiveness of reducing data transfer. So the distributed in the graph rendering application, each node renders a portion of the entire screen, and excuse me. And as for the computations, so the different nodes might need to copy the physical objects around between different nodes. And the x-axis shows the number of different nodes. And as you can see that if we only have a single node, there's no communication. So the baseline approach just simulates our original solution, which is doing all the I/O inside a task, so that every task needs to fetch the external data for every task. And the Legion plus external resource version applies the optimization of reducing data transfer cost. And as you can see that our new approach spends the same amount of time doing the computation, but we actually could save a lot of computation cost and achieves up to 50% speed up. So the next optimization we applied is the write after read optimization. So assume that I'm sorry. Sorry for that. So any questions so far? Okay, here we go. So the write after read optimization says if you have a region that is attached to some external instance, and you have some tasks that has been mapped to the other nodes for parallel execution, and the acquire and release operation will allow the Legion to make some local copies. And so the beginning is the same as the previous optimization, but the difference is that. The difference is that, so the first is a read-write task, and which may change the content in the local instance. And upon the completion of the read-write task, Legion's dependency analysis knows that before release operation, there is no read-write task, which means that the local instance won't be changed by read-only task. As a result, Legion could perform the release operation before the completion of some read-only task. And as a result, Legion runtime could actually flush the dirty data back to external resource even before the completion of some read-only task. And if there are some read-write task, because the dirty data has been flushed back to the external instance, Legion runtime could start to schedule some read-write task on different nodes. And as a result, there could be read-write task runs in parallel with some read-only task. Even there are some data dependency between that, because these two tasks are using different local copies of the data. And by doing this, we could achieve more parallelism. And we have a database micro benchmark for evaluating the write after read optimization. So the application randomly performs read-only queries and read-write queries on some external databases on disk. So the x-axis shows the percentage of read-only tasks. So we just want to know what happens in different scenarios. So 0 means all the tasks are read-write tasks, and in this case, because there are dependencies between any two tasks, so there is no parallelism opportunities. So our optimization version has the same behavior as the baseline approach. And, and one means all the tasks are read-only tasks. And because there is no read-write dependencies, and so all the tasks could be executed in parallel. So the baseline approach also achieves the same speedup as our optimization version. And the write after read optimization could be applied in the middle case when we have both read-only task and read-write task. Our optimization could actually achieve small parallelism, and which enables up to 30 to 50% speedup. So we also evaluated our integration of external resource on S3D, which has been mentioned in the previous talk. It's a production combustion simulation. So the S3D has to checkpoint some intermediate result after a fixed time step. And so we have tested in 3 approaches. So the orange bar shows the Fortran implementation. And I think the purple bar shows our original Legion implementation, which is doing the checkpoint inside some Legion task. And the blue version shows shows the behavior of the attach operation. So the bar actually shows the checkpoint overhead in percentage of the baseline simulation. And as you can see, please notice that the Legion implementation of S3D is actually 7 times faster than the Fortran version. So actually, the Legion and Fortran version spends the same amount of time for doing the checkpointing. And it is just because the Legion execution is faster, so that the overhead of doing checkpointing in original Legion is 7 times higher than the overhead of doing checkpointing in Fortran version. And the blue bar shows the attach. Please. Yes.
My question was whether the Fortran version used MPI-IO, and the answer is yes.
Yes. So the Fortran version uses MPI-IO. And as you can see that after applying the optimizations, we could achieve almost negligible overhead, even in the case we are doing some crazy checkpointing. So this, I think no question makes me able to finish my slides actually several minutes before the expected time.
I don't think anybody will object. But we have time for questions if people have questions.
Can you talk a little bit about the motivation for the serialized and deserialized methods? Why did we decide to include those?
Mm-hmm.
My question, can you talk a little bit about why we decided to include the serialized and deserialized methods?
Okay, so the question is why we need to involve the go back. Okay, so the question is why we decide to involve the serialization-deserialization method in Legion. So this is because I think because there are cases when the data format is not understandable by Legion. So consider that. So for example, there could when we do the graph rendering application. So actually, the objects are irregular data because different objects may have different texture in different size. And because Legion has a uniform assumption that every element has the exact same size, but this may not be true in some cases. So in this case, so our solution is just the field just holds a pointer to the actual opaque data structure. But in this case, the copy operation doesn't work because you cannot just copy the pointer between different nodes, because the pointer makes no sense. And what we actually need to do is actually copying the logical content inside the data structure. So in this case, we need the serialization and deserialization stuff around. So any other questions? Mm-hmm.
There's one other use case for the serializer stuff that we want to use, and that's sometimes you have data which effectively maybe compressible, in the sense you may have like was it the old fluid animate benchmark from Parsec has these big cells which have some number of particles in them, and it's silly to copy around the whole cell when quite often there's only a few particles there. So this serialization would basically let you save network traffic by basically compacting out the don't care bits and then reconstructing the original structure on the other side.
Is there any integration planned with these deserialization with your, I don't know, dependent partitioning or some of the ideas that you presented?
Well, so the whole idea of being able to stuff irregular opaque objects into regions is so that we can use exactly the existing partitioning logic, exactly the existing dependence analysis logic, all the other stuff by basically making it fit within our data model, even though it's fitting in by having pointers outside the model. All the other stuff is designed to come for free.
Any other questions?
Any other questions?
Okay, go ahead. Yeah, one more.
Is it possible to partially preserve the data in
I'm sorry?
So sometimes I think user might
Okay.
So is it possible to partially serialize some elements in the arbitrary struct, not whole things?
I didn't get.
So
Sorry.
is it possible to serialize some partial elements, not the whole thing in a struct?
The question is it possible to serialize the partial fields?
Yes, but partial elements, not the whole field in a struct.
Yeah, so you can choose to serialize only a subset if you want, but then the stuff you don't include, you better not need.
You cannot deserialize the stuff that is not involved. So actually, I think the application could decide to just transfer partial of the data. So that's just compression techniques. So you can just serialize the important bytes into our serialization. But the disadvantage is that the data that is not included in the serialization, you cannot deserialize them and create the instance on the remote nodes.
Right. So the other way of answering this is that the model in Legion is that fields in a field space, an individual field is kind of indivisible. Whatever you say is one field is the unit that we're going to move around for that.
Yeah.
And so if you have a complicated data structure which you want to be able to move pieces of, then maybe what you really want to do is have a couple fields, each pointing to the corresponding piece of your opaque data structure. And then you can ask us to move individual pieces of it. But if you say to move a field, we're going to move whatever that field is. And in the case of the custom serializer, we're just going to call your serializer and it's going to do whatever you told it to do.
Mm-hmm. Go ahead.
So the question I would like to ask is, what took me so long? This is a fantastic feature that I felt like Legion needed when I was working with it. So what you basically described here is a non-intrusive serialization framework as opposed to an intrusive one. And a lot of other runtimes mix intrusive and non-intrusive serialization frameworks. The advantage of intrusive serialization framework is obviously that it's a lot easier to do hierarchical serialization of your types. Mm-hmm. Do you plan to provide some sort of intrusive interface later, or just stick with only the non-intrusive?
Okay, that's a very good question. So the question is, do we plan to provide some non-intrusive serialization stuff? So actually, this serialization stuff is ongoing, and it's going to be. So I'm actually actively working on this part, and this part is also going to be integrated into our new DMA subsystems. So for now, I think I think we could consider. So we haven't thought about this question, but I think we could consider applying that part into Legion.
So I wanted to add two things. First of all, one of the reasons you're seeing this is because exactly of the feedback you guys gave. So
Yeah.
the feedback
Yes.
is useful and actually, has non-zero impact on what we do.
Yeah.
But the second one is, one reason for cutting it like this is, again, trying to be very careful about not baking policy decisions into what the Legion model supports, right? You can put an intrusive serialization framework on top of this, right? We haven't taken anything away by doing this. Whereas if we assume an intrusive one, then we are taking some of the choices away from the programmer or from the DSL or from the third-party library. And so this is intentionally a minimalist approach. And as we find that there are common cases sitting on top of it that programmers would like to have be automated, the question then becomes, is it something that should be baked directly into the runtime, or is it into the programming model, or is it something that should exist as a library that's available for application use but still conceptually above the programming model boundary?